Alright, this video is going to be about the mean value theorem and Rolle's theorem, which are related to each other. Rolle's theorem is just a subset, it's a special case of the mean value theorem. So this is the big theorem, and then Rolle's theorem is just a special case of it. I already have a picture drawn for us, so let's read the rule, get confused, look at the picture, and then hopefully it'll make a little bit more sense. Mean value theorem, which is abbreviated MVT. You have two conditions that need to be met before you can use this theorem. First of all, the function must be continuous. It's pretty much true for everything in calculus. We want the function to be continuous. And then second of all, now that we know derivatives, we also want the function to be differentiable. So we don't want any sharp turns, or we don't want any cusps. We definitely don't want any discontinuities or no vertical tangents, right? We want it to be smooth and continuous, right? Basically like a polynomial type of graph. So yeah, got to be continuous, got to be differentiable. There's no real math to do for that. You just kind of have to look at the function, investigate it mentally, and think, is it continuous? And then say, check, yes, it should be. And then look at it, is it differentiable? And then say, yes, check, it should be. And then here's what the theorem says. If your function is continuous and differentiable, then there is at least one number c, and that c is an x value. It's going to be in your interval, so it's going to be between a and b, the left side and the right side. And it's going to state such that f prime of c, the derivative, the instantaneous rate of change, the slope of the tangent line, f prime of c is going to equal f of b minus f of a over b minus a. There is going to be one point in your interval so that the derivative at that point is equal to the average rate of change, right? F of b minus f of a. That's the slope of your secant line. So if you were to think about this, right, that's just the slope between the points a and b. Your average rate of change. What this theorem says is, at some point on this function between a and b, there's going to be a point in the middle where the instantaneous rate matches it, right? There's going to be a spot where the derivative is the same as that average rate of change. Or another way to think about it, the instantaneous rate of change at x equals c is going to equal the average rate of change from a to b. Right? Your average rate of change is the slope of the secant line. Your instantaneous rate of change is the slope of the tangent line. Or if you want to think about it more geometrically, you could say the tangent line at x equals c is going to be parallel to, right? Same lines that have the same slope, they're parallel to the secant line from a to b. So I've kind of got this function just sketched. We got the 2 points. What this mean value theorem says is somewhere in the middle, the derivative, the instantaneous rate, slope of tangent, somewhere in the middle, that derivative is going to match. So let's look. I'm going to just put this pencil down. If I were to pick a point here, like super close to the a, like I could draw that tangent line, but it doesn't look like that tangent line is very close to being parallel to the given secant. Or if you were to pick a point like over here, which is kind of close to the b value, think about what that tangent slope would be, and like, oh, okay, that doesn't match. But what this theorem says is, at some point on this function, there's at least one spot where the tangent is going to match. And it looks like maybe that point, maybe it would be around here, right? And if you were to draw the tangent line that just touches and grazes the function at that one spot, it looks like the tangent line at that specific point is going to be parallel to the secant over your interval. Right? So what this theorem says is there's some number in my interval, there's some c value, so that the tangent, the instantaneous rate, the derivative, at that point is going to be the same as your average rate of change, which is your slope of the secant line. Right? So it's a little bit weird, but mathematically these are pretty easy questions, and we'll see one on the next page. But at some point in the middle, the slopes are going to match, right? You have your average rate of change, you have your slope of the secant. At somewhere in the middle, in your interval, the derivative, the instantaneous rate of change, the tangent slope, is going to match it. Now, Rolle's theorem is a special case of this mean value theorem. Let's go look at it. It has a third condition. Of course, it still needs to be continuous, still needs to be differentiable, just like mean value theorem. But Rolle's theorem has this extra condition where the left height, f of a, if you plug in a, which is the left side, if you plug in a and you plug in b, you need to get out the exact same number. So f of a and f of b being equal means, hey, those 2 points are the same height. Now let's think about something. If I were to do my secant slope, right, f of b minus f of a over b minus a, that's the slope between those 2 points. That's your average rate of change. If f of b and f of a, if they are the same thing, like if they're both 5, 5 minus 5 would be 0, right? Think about the secant slope between those 2 points. Since the left and the right side, they're at the same value, when you find that secant slope, I know the secant slope is just going to be 0. Right? So Rolle's theorem is nice. It just says at some point in the middle, there's going to be a value, c, and that c is in your interval. There's going to be some point where the derivative is 0. It's just a special case of the mean value theorem, right? But instead of these 2 points being at different heights and then having that slope in between them, and that slope going to match in between them, well now, if those 2 points are at the same height, now I know there's going to be at least 1 point in the middle where the tangent is going to match. But if those 2 points were at the same height, now I know that slope is specifically going to be 0. So Rolle's theorem is just the easiest case. It's the special case of the mean value theorem. If you have the f of a and the f of b, if you know those are the same, then you know those 2 points are at the same height. That means your secant slope is 0. So you can kind of just jump straight to setting the derivative equal to 0. Or if you want to think about it more algebraically, the instantaneous rate of change at x equals c is equal to 0. Or if you want to think about it geometrically, you could say the tangent line at x equals c is horizontal. Okay, so Rolle's theorem, just a special case. It's a subset of your mean value theorem. Let's go work a question. Show that the conditions for Rolle's theorem are met and find the c value that the Rolle's theorem guarantees. And then it gives you the function and it gives you the interval. Okay, wonderful. First thing you always need to do is check, is the function continuous? Is the function differentiable? And there's no real math to do for those two, right? You're just going to look at it and you're like, hey, like that function is a polynomial. So by nature, I know that it's going to be continuous and I know that it's going to be differentiable. It's a polynomial. Yes, so it's going to be continuous. And it's going to be differentiable. There's no math to do. Just show me continuous check, differentiable check. Show me that you're acknowledging and you're thinking about the conditions, but there's no math to actually do to prove them. Okay, now let's do the third one. I need to check f of a and f of b, and those two must be the same. So let's plug in -2, and then let's plug in 3, and let's see what those values are. If I plug in -2, I would have 4 minus -2, so plus 2. Minus 6, that would be 6 minus 6, ooh, is 0. Okay, that's nice. Looks like we got an x-intercept at -2. Let's plug in 3. 3 squared would be 9, minus 3, minus 6. Well, it looks like those are both 0. It does not matter what these numbers are. Like they could both be 0s, or they could both be 7s, or they could both be -9s. It doesn't matter what these are. It only matters whether they match or whether they're different. And if they match, you can use Rolle's theorem, right? So therefore, all conditions are met, and you can use Rolle's theorem. All conditions met to use Rolle's theorem. Continuous, you just put check. Differentiable, you just put check. But there is math to check and to show for looking at the endpoints. And when you plug them in, plug in that left side into the function, plug in the right side into the function, you need to get out the same value. The fact that they were both 0s, that only tells me that they both happen to be x-intercepts. Like if you're thinking about this graph, you have the intercept at -2 and then the intercept at 3. Wonderful, right? It doesn't matter, though, at what y value those 2 points are. It just matters that they're at the same y value. Okay, now what this theorem says is at some point in the middle, the derivative is going to be 0. So these are really easy. You just set f prime equal to 0. These are pretty easy questions, right? So let's go for it. The derivative here would just be 2x minus 1. For Rolle's theorem, I'm just going to set the derivative equal to 0, right? I'm not plugging in 0. If you plug in 0, that's finding the slope when x equals 0. We want to figure out where is the slope going to be 0. So you set the derivative equal to 0. Then you can solve it. Add the 1, divide by the 2. It looks like your x value is 1/2. And then let's check. Is 1/2, which that's my c value, is 1/2 in my interval? Is that between my left side and my right side? Yes. And of course it's going to be, right? Rolle's theorem guarantees that there's going to be at least one. There could be multiple solutions that work. There could be 5 solutions, and maybe one of them is not even in your interval. That's okay. But what Rolle's theorem says is there is at least one that will be in your interval. If you happen to find extras, that's just wonderful. If you happen to find some that are outside your interval, that's fine. But there's going to be at least one that is in your interval 100% of the time, every single time. That is guaranteed by Rolle's theorem. Right? So check the conditions. Continuous, check. Differentiable, check. Got to plug in the endpoints and confirm that they're the same. Right? That means all the conditions are met. You can use the theorem. But then the actual math that you do for Rolle's theorem, you take the derivative, set it equal to 0, and you solve. It's a very quick, very easy question. Do not miss Rolle's theorem stuff, right? I know it's weird because it's a theorem and we don't really do a whole lot with these theorems, but mathematically they're the simplest things that we do all year. Take the derivative, set it equal to 0, solve it. Okay, now the next one's going to be a mean value theorem question, which is only going to be slightly harder, right? Let's read it and try to answer it. Given the function 3 minus 5 over x on the interval 1 to 5, which has the graph for us, let's plot the points. Here's the point at 1, 1, 2, 3, 4, 5. Here's the point at 5. So you really don't care about anything else, right? This function does have an asymptote, right? Has the asymptote at x equals 0 over here, but we just don't really care about it because it's not in my interval, so I don't care, right? It is discontinuous at 0, but you only need it to be continuous in the piece of the graph that we were looking at, right? So let's see, part A, it says visually, what is the mean value theorem trying to find? Let's draw it. Well, let's think. Here's your secant slope, right? The slope of the line that connects those 2 points. What mean value theorem says is at some point in the middle, at some point on this function, the tangent slope, the derivative, is going to match. Can you kind of see where it is? It's not usually super close to the right, nor is it usually super close to the left. It's usually somewhere kind of in the middle-ish, but there's going to be at least one point where that tangent at that point, let's see, it probably looks like it's about here. If you were to draw the tangent at that point, it would have the same slope as what your secant was, right? So there's one point on the line where the instantaneous rate equals the average rate. And then we want to know, what is that x value where the tangent matches the secant slope? Okay, so we did that. Here we can write it also. There's some x value between 1 and 5 where the tangent is parallel to the secant from 1 to 5. Okay, so that's wonderful. Let's do the math. Has to be continuous, which it is, right? We can visually see this graph. We also have the equation. I know it's got to issue at 0, but 0 is not in my interval, right? So it's continuous for 1 to 5, and it's also differentiable, right? Again, I can see that all visually from the graph, right? It's smooth and it's continuous, right? Smooth means differentiable. Continuous means continuous. And if you can see the graph, yes, definitely continuous check, differentiable check. So I know mean value theorem applies. Now remember, for Rolle's theorem, you just set the derivative equal to 0 and you solved it for x. We're going to do kind of the same thing. We're going to take the derivative and we're going to set it equal to something, but I have to figure out what that secant slope is, right? We're trying to figure out where does the derivative match the average rate of change. So the first thing you do is find what that average rate of change is. I find the slope of that secant line. I find that average rate of change. And then I'm going to set that derivative equal to that number, right? So whatever that secant slope is, if it's 5, you set the derivative equal to 5. Or if the secant slope is 3, you set the derivative equal to 3. Or here I think this secant slope, if you count it, up 1, over 1, up 1, over 1, I think that secant slope ends up just being 1. And if we needed to, we could calculate it. So we find the secant slope, f of 5 minus f of 1 over 5 minus 1. Remember, that's your average rate of change from 1 to 5. I find that secant slope, which here it's 2 minus negative 2. And then 4, 0, I'll just leave it as the 4. So that's 4 over 4 is 1. You could visually just count it. It goes up 1 over 1, up 1 over 1, up 1 over 1. The slope of that line is 1. Or if you do your rise over your run, that also gives you your secant slope. So I found the secant slope, and it's 1. So now I'm going to set the derivative equal to 1. Whatever that average rate of change is, you set the derivative equal to that number. Rolle's theorem is easy because I know if those two would have been the same, the secant slope would have been 0. So I can kind of skip this step and I just jump straight to setting the derivative equal to 0 because for Rolle's theorem, the slope is 0. But for mean value theorem in general, you have to figure out what the slope is, and then you set the derivative equal to that number, and then you solve it. Okay, so let's go back and let's take this derivative. I'm going to do it up here. Here's your original function. It's 3 minus, let's get that out of here. It's 3 minus 5x to the negative first. So if I wanted to take the derivative of 3 goes away, so that's fine. That negative 1 is going to multiply, so it's going to be a positive 5x to the negative second power. So here your derivative is 5 over x squared. So I would take that derivative, now just set it equal to 1. Cross multiply. It looks like you're going to get potentially two solutions, the negative root of 5 and then the positive root of 5. Now let's think. I really don't care too much about that one. The answer that this question wants is this one. Why don't I want that one? Not in my interval, right? We only care about this graph specifically between 1 and 5. So that square root of 5, which would be a little bit bigger than 2, let's look at it, right? Here's your x value. There's 1, 2. It does look like at that point that we had thought the tangent was going to match. That does look like it was slightly bigger than 2, which we just mathematically proved is the root of 5. And then yes, the root of 5 is between 1 and 5 for sure. It's going to happen. There's at least one solution where the derivative is equal to that secant slope. There's going to be at least one solution in your interval. You could have multiple. You could have some that are not even in your intervals, but you don't really care about those. What mean value theorem guarantees you is there's going to be at least one in the middle of your interval. Okay, last example for this video. You are driving a car traveling on an interstate highway at 50 miles per hour. You pass a police car. 4 minutes later, you pass a second police car, and you're again traveling at 50 miles an hour. The speed limit on the highway is 60. The distance between the two police cars is 5 miles. The patrolman in the second car gives you a speeding ticket for driving 75. How can he prove that you were speeding? Well, okay, let's kind of draw a picture. You've got this car. I can't draw a car, so I'm just going to draw a box. At that one instant, you were going 50 miles per hour, and we'll just call that time equals 0. And then later on, right, you were driving, and you were again going 50 miles per hour. We'll consider that to be 4 minutes. So you're going 50 both of those instances at time equals 0 and at time equals 4. You pass the cop number 1, you pass the cop number 2, and then of course the distance in between them, it tells me was how long? 5 miles. There it was. I was looking for it, couldn't find it. So let's think. Why can this police officer give you a speeding ticket for going 60? Well, let's think about the average rate of change. What's your average speed? So you're changing your distance over your change in time. If we travel 5 miles in 4 minutes, right, the distance between those two spots is 5 miles. The time that elapses between those two spots in this journey was 4 minutes. So I know if I wanted to find my average speed of that journey, you take your distance divided by time. Let's convert this to hours. So 4 out of 60, so that's 1/15 of an hour. So I have 5 miles over 1/15 of an hour. So your average speed, if you travel 5 miles in 4 minutes, your average speed is 75 miles per hour. right? And we did that just using some basic geometry, right? Rise over run, change in distance over your change in time. So how can he prove that you were speeding? Well, by mean value theorem, there must be at least one time in your interval where your instantaneous speed equals your average speed, which was 75 miles per hour. So they could really prove that you were going 75 miles per hour mathematically, right? And the reason why is mean value theorem. Logically, we know it could even be worse, right? To cover 5 miles in 4 minutes, you would have to be going 75 miles per hour every single second, right? And then that's how you could cover that distance in that amount of time, if you were going 75 every single second of that journey. But we know you started off slower and you ended up slower. So we know at some point he was probably going, I say he, you don't really know, it just says you. We know if you start and end at 50, and if your average is 75, well, at some point in that journey, you were going much faster than 75 to offset the areas in that journey where you're lower, right? So if it was 75 the whole 4 minutes, then you'd get from A to B. But since we know you started below and you ended below, we really know you must have been going faster. We can't really prove how fast you were going, not yet with only the derivative stuff that we know. But we know for sure there's at least one time. If your average is 75, then logically we know and mathematically we can prove that there's at least one time when you were going 75, and that's your mean value theorem. Okay, let's do the part B, and then we'll be done with this video. You foolishly argue with the patrolman who is writing you your speeding ticket, and he calls his brother who is currently taking calculus. Oh, bad news. And he just learned the mean value theorem. All right, so you're busted. But now the patrolman rewrites your ticket, and he's going to charge you for going 65 miles per hour twice. And then how can he prove this? Well, again, let's think. We know at time equals 0, you were going 50 miles per hour. Now, I don't know what that middle time was, but I know there's at least once when you were going 75, right? And we know that because of the mean value theorem. There's some time in the middle, for sure, 100% guaranteed, where you were going 75. And then I know at the end, at time equals 4, we were going 50 miles per hour again, right? So the speed of my car is continuous. Speed is continuous. You don't just jump from 50 to 75, right? It's gradually going to rise. So how can we prove that you were going 65 twice? Well, that's where the IVT, the intermediate value theorem, comes in. By IVT, there must have been at least 2 times where you were going 65 miles per hour. If you start at 50 and then you have some unknown time where you're at 75, right, you're going to have to pass 65 in that acceleration phase. And then you're going to have to deaccelerate to get back down to 50. And so we know, hey, to get from 75 back down to 50, you're going to have to pass 65. Once during the acceleration and once during the deacceleration. Now, could we, right, that's the done, we're done with this question, right? IVT, yes, you can prove that you were going 65 twice. Since you start at 50 and you go up to 75, you got to pass 65 once at least, and then you're at 75, go down to 50, you know you have to pass the 65. Could you also prove, like if you had a really nice police officer, could you also prove that you were going 51 miles per hour twice? Yes. What about 60 twice? Yes. 65 twice? Yes, we just did that one. Could you even prove that you were going 74.99999 miles per hour twice? Yes, every single value between 50 and 75, you know you're going to hit it once in the acceleration phase and then a second time during the deacceleration phase. Technically, knowing only the math that we know right now, we can only prove that you hit the 75 once, and that's your mean value theorem. That was the part A. Later, once we learn more calculus, we'll be able to prove that, hey, he actually went more than 75, and if he goes more than 75, therefore he actually hits 75 twice. But right now, knowing only the derivatives, we're kind of handcuffed. No, there we go. With what we can do. So 75 once, that's your mean value theorem. And then anything in between the 50 and the 75, yes, you are guaranteed to hit twice. And that one's because of your intermediate value theorem.